LeetCode 14. Longest common prefix might seem like a simple string check, but it mirrors real-world problems like autocomplete in search engines, URL routing, and deduplication in file systems. When scale kicks in, every character scan adds up. So how do we go from slow scans to smart solutions? Let's jump in. Okay, ducklings, let's kick things off with a brute force pass. We'll walk down each column of characters one step at a time until something breaks. Let's build it out in code and see how far it gets us. First, we guard against edge cases. If the input array is null or empty, there's no work to do. We just return an empty string right away. With valid input in hand, we start comparing characters from the first string, because any prefix must start there. We'll move through each character by index. For each index, we pull the character from the first string. This will be our reference to check against the same position in all other strings. Now we compare that character across all remaining strings. If every string matches at this spot, we keep going. But if any string ends early or mismatches at this index, we've hit the boundary of the common prefix, so we return the slice up to this point. If we make it through every column without breaking, that means the entire first string is a valid prefix, so we return it as is. This brute force approach runs in big O of S, where S is the total number of characters across all strings. With 200 strings of 200 characters, that's up to 40,000 comparisons. Space stays big O of 1, just a few pointers in action. But can we cut down on repeat work? Instead of checking column by column, let's shrink the prefix string by string, like trimming tail feathers. Here's how we sharpen the brute force. Edge cases first, again. If the array is null or has 0 strings, there's no prefix to look for, so we return an empty string immediately. We take the first string as our starting guess for the prefix. It's just a guess. We'll whittle it down as needed. Next, we loop through the rest of the array and check if each word starts with our current prefix. If a word doesn't start with the prefix, we trim one character from the end and try again. Repeat until it fits. While shortening, if the prefix gets wiped out completely, that means there's no shared prefix, so we return right away. Once we've validated the prefix across all words, we return what's left. That's the longest prefix shared by the group. This method also runs in big O of S, still tied to total character checks, but trims down redundant comparisons. Space is big O of 1. A tighter, cleaner approach for real-world inputs. But even here, we're still checking characters again and again. Let's do better by cutting down those checks, using binary search on prefix length. We begin with another quick safety net. If the input array is null or empty, we return an empty string instantly. To guide our binary search, we need a cap on prefix length, so we find the length of the shortest string. No prefix can be longer than that. With our bounds set, we set up binary search from length 1 to the shortest word's length. We're testing how long the common prefix can be. In each binary search step, we test whether a prefix of mid-length is shared across all strings. If the prefix works, we try a longer one by shifting the window up, searching for something even better. If it fails, we know the prefix is too long, so we adjust the window down to test shorter lengths. When the search ends, we've zeroed in on the maximum valid prefix length, so we return that slice from the first string. This helper function checks whether all strings share a prefix of the given length by comparing substrings. We scan the rest of the array and check if each string starts with the test prefix. If one fails, we bail with false. If every string passes the check, we return true. The prefix is good for all. Binary search gives us a time complexity of big O of S times log M, S for total characters, M for the shortest word's length. That's around 320,000 checks at most with 200 strings. Space remains big O of 1, making this clean, fast, and perfect for interviews and production alike. We began with brute force, slow but clear. Then trimmed prefixes smarter, cutting waste. Finally, binary search let us leap straight to the answer, slashing operations down dramatically. Why does that matter? In real systems, this kind of efficiency powers instant autocomplete, lightning-fast APIs, and scalable data tools. These are the moves top-tier engineers rely on. And now you've got them too. So what other string problems could you supercharge with binary search? Go explore and keep leveling up.